So what's happening at some point is that we now have an extra proton on the carbonyl oxygen, the red one here, plus charge. The other oxygen now is neutralized. Okay. So this step right here is called solvent-assisted proton transfer. Solvent-assisted H plus transfer. So anytime you need to get a proton from one part of the molecule to another part of the molecule, just move it and put H plus transfer. Yes?
Do you show the, like, being pulled off if that helps you?
Absolutely. Yeah, absolutely. Okay. This is good for us getting towards the acetal because we now have the OH group formed into a leaving group, which is water. Okay? So now water can take electrons and leave. Takes the electrons from that carbon-oxygen bond and it leaves. And that gives us a carbocation, which is resonance stabilized. So water leaves, we've added water, or we haven't added water. Water is released, and we have a proton. Oh my gosh, sorry. Let me start over. Water has been released, and a carbocation has been generated. Okay? And I just said a second ago, this has a resonance stabilized form where the lone pair on the oxygen comes down and forms a pi bond. So that's a resonance form. You don't have to draw it, but you can. Understanding it's there is the most important thing. Okay? So we've, yeah?
I think, I'm not sure, but I think we learned it as the oxygen gives creates a double hole.
Like this?
Yeah.
Yep, that's showing this resonance.
Okay.
Yeah.
So it's the same thing?
It is the exact same thing, and I'll do those for you. So lone pair comes down, kicks off that, and that will take you to this resonance form. Okay? Good? Yeah? That should be an arrow. Okay. So we have released one water molecule. We have excess of the alcohol, right? So that one water molecule versus maybe 100,000 alcohol molecules. The alcohol will most likely outcompete as a nucleophile. Okay? So if water adds back in, we just go back this way. But if the alcohol adds in to the carbonyl carbon, we now have a second carbon-oxygen bond. And that oxygen brought along with it the hydrogen as well as the R group. And so it now has a positive charge. I changed colors on you here. That's not fair. Let me go ahead back here. There you go. Okay. So once again, we're under acidic conditions. We have protons coming on and off and on and off and on and off. But eventually, something will come along. For example, another alcohol molecule that will pull off this extra proton.
Can you use water too?
Absolutely. There's just more of the alcohol around.
Okay.
Absolutely. Electrons will go back to the oxygen, and that will give you your final product, which is the acetal. Make sense? Okay. All very, very, very good questions. So yeah, there's a chance that water molecule could pull off the proton. There's a chance it could add back into the carbonyl carbon. All of those things could happen. Yeah. Okay. Good? Okay. So acetals, you're going to see this a lot. Anybody taking biochemistry in the future, possibly? Okay, this is your sugar chemistry right here. Okay, so a disaccharide is held together through the formation of an acetal. Okay, that's how these are formed. You guys look so excited about sugar chemistry now. No?
Oh, yeah.
Oh yeah. Okay. So your sugar, actually, I don't know if you guys talked about this at all. Your sugar exists in two forms, an open form and a closed form. The open form is an aldehyde or a ketone, depending on the sugar. Closed form, hemiacetal. So it is the back and forth of basically, actually right here. It's the back and forth of this equilibrium that's happening. Okay, so carbonyl acetal, hemiacetal, sorry. Carbonyl hemiacetal. And eventually, if you join two together, you will get a structure, please don't draw this, where you will have two sugar molecules that are joined together. Oh gosh, that's my worst chair right there. Oh, ugly. And you will have other sugar molecules all joined together. Ooh. And here is the formation of acetals. Fun, huh? That's ugly, really ugly. Please don't draw that. Okay, I'm actually gonna erase it so it's out of our history, our memory. So that's where this is gonna come up a lot, is in that type of a situation. I'm trying to think what other biological molecules. Polymer chemistry is starting to use those more and more because they can be so strong, but also reversible. So a lot of your more environmentally friendly polymers are based off of this type of chemistry, where they'll use starch-based polymers in order to make things like straws and forks and knives and things like that, because those are also just sugar molecules strung together by these types of functional groups. Okay, so let's take a second and try to predict what the products are for this reaction. Okay, so this reaction is performed under two different conditions. We start with propanal, 3-carbon aldehyde propanal, and in each case, I'm going to react it with an oxygen nucleophile that has an isopropyl group attached. I'm saying that kind of in a way that I'm not giving anything away. So take a second, you can work with people next to you if you want to. Ask yourself, what type of conditions am I under, and what type of product would this form? Okay, and then try to draw that. Okay. There we go. You doing okay? Okay. So what's the difference between these two? What type of conditions is the first one under? Acidic, right? So this is acidic. So that means you can make OH can be made into leaving group. Can be made into leaving group. Okay. So that means if you can make the OH into a leaving group, then that means that you can add 2 of the alcohols, right? Okay. Second one is under basic conditions. Okay, so once again, a good way to recognize that is you see this metal right here, you see potassium. If you see potassium, lithium, or sodium, they're all kind of, oops, sorry, that's not potassium, that is. They're all giveaways that you have a salt there, which means they are a positively charged ion, and it's going to be balancing out a strong nucleophile or base that has a negative charge. Okay? Negative charges are going to be your basic condition. Positive charges are going to be your acidic condition. Positive charge, let me be very specific, positively charged proton, some acid source. Okay? All right, so if we have acidic conditions at the beginning, our product is going to incorporate 2 of those nucleophilic oxygens. And we end up with the incorporation of 2 of those alcohols, and you end up with something crazy like this. Is that what you got? Sweet. Any questions on that? All right. So under basic conditions, we cannot make OH into a leaving group, make OH into leaving group. Therefore, you have one addition. It's my shorthand for addition. So that means that the OH will still be present, and that is the oxygen that was originally from our aldehyde. And we will incorporate 1, use a different color here, of the alcohol groups into our product. Good? You may have drawn it slightly differently, that's fine. Okay? But the main thing is you have 2 OR groups under acidic condition and 1 OR group and 1 OH group under basic conditions. Sweet. Good? Okay. All right. Next one's a different way to kind of think about this. And that is, let's predict what the starting material look like. Okay? So in this product, we have formed an acetal. Oh, we have formed an acetal. Okay, I recognize the fact that I have 2 OR groups on the same carbon. Oh. Make sense? We have an acetal. So let's map out where this nucleophile is in our product. It's a 2-carbon group with an oxygen, 2-carbon group with an oxygen. Okay? They're both now attached to what? They're both attached to a carbon, which was what? What was that carbon part of? What is it? A carbonyl. Good. So thinking backwards, everything that I'm highlighting here in yellow was in my starting material, right? The blue highlights were from the new bond, and everything in pink came with the nucleophile. So that means my starting material had the 5-membered ring. And the spot where the two alcohol groups are added in was the carbonyl. Good? Sweet. All right, any questions about acetals, hemiacetals, acidic or basic conditions? No? Okay. That's the same page. So let's talk about nitrogen nucleophiles. Okay. Most of the time when we add nitrogen nucleophiles to carbonyls, it's going to be under acidic conditions. I cannot think of adding it under basic conditions. Okay? And usually the reason why nitrogen nucleophiles are being added is because we want to change the carbon-oxygen double bond into a carbon-nitrogen double bond. That's usually why we're doing this. Okay? So nitrogen nucleophiles tend to take carbonyls and make them into carbon-nitrogen double bonds. Okay? But nitrogen, unlike oxygen, makes 3 bonds, right? So that's going to come into play with what type of product we get out. If we have a reaction with ammonia or a primary amine, which is an amine that only has one R group attached to the nitrogen, we will just do a swap, meaning we will swap the carbonyl oxygen for nitrogen. Okay? We lose the oxygen that was attached to the carbonyl. We lose that as water. Okay? Those 2 hydrogens, to balance this equation, come off of the nitrogen, and the nitrogen is left with whatever the last group is, meaning in this case, it's going to have the R group attached. If we used NH3, it would have 1 hydrogen still attached. Does that make sense? I know I'm doing this kind of fast. Okay? So why is it always under acidic conditions? Because we need to make the oxygen leave. Okay? How do you feel about this mechanism? Give me one of these if you're like, let's do it. Okay, we're gonna do it. Okay, very similar to what we had with the addition of alcohols under acidic conditions. We have a weak nucleophile, so we need to make a super electrophile. So we're gonna start off I have highlighter on. We're gonna start off with the oxygen using 1 lone pair to make a bond to hydrogen. Okay, these are all reversible steps. So now the oxygen has 1 lone pair, 3 bonds, which means it has a plus charge. Okay. So we can draw the resonance form if you would like, or we can have our nucleophile, which is the nitrogen, attack at this point. So we have a super electrophile. It is a full positive charge. It attracts the negatively charged electrons in the lone pair, okay? So lone pair is going to attack the carbonyl carbon, pushing electrons up to the oxygen. Once again, if you want to, if it makes more sense to you, draw the resonance form where we have the full positive charge on the carbon, and you can have your nitrogen nucleophile attack right there. Okay, either one is fine, but you don't have to do both. So I'll put this in parentheses here. Don't have to put. Okay, everybody good? All right. So what have we done now? We've made a single bond between the carbon and the oxygen. We've reduced that, and we've made a new carbon-nitrogen bond. So we have all of our original structure. Now we have a single bond to oxygen, which now has a proton on it. We've made a new bond between nitrogen and carbon. It brought with it a ethyl group and 2 hydrogens. And it is now positively charged because it shared its lone pair. Okay. It can pop off, it'll pop on, it'll pop off, it'll pop on. At some point, the proton will come off of it and a proton will get put onto the oxygen. So this will undergo an H plus transfer. Okay, and that will make your leaving group. Okay, good. I don't want to confuse anybody by simplifying this step, so please let me know if that simplifies it too much and it confuses you by saying just H plus transfer. I'm happy to draw in the detail if you want. Yes?
Can you draw in detail?
Sure, absolutely. So the detail in this case would show, okay, I'm gonna put it in different color. So the detail would show another molecule of our nucleophile coming and pulling off that proton, okay? At the same point, or at some point, the oxygen will grab a hold of that proton, a proton, okay? You can show this in 1 step, you can show it in 2 steps, you can show it in 3 steps if you want to. Does that help?
Yes, yeah.
You sure? That was a
Yeah.
tentative yes.
I
What
understand-
looks different
I
to you?
understand it, well, I'm just like a little confused on.
Sure.
But I guess it's like, there's just excess, like, just exists.
Yes.
And
Yes.
This is where it's like.
Yes.
Okay.
Yeah, in order to drive the reaction, there has to be excess.
Yeah.
Yeah,
So-
yeah. And it's our laziness as organic chemists for not saying, like, you have 3 equivalents of blah.
Yeah.
It would be really helpful for us if we did that, yeah. What I will say to you is this. If I don't specify 1 equivalent, you can assume you have excess, okay? I'm gonna put that up here. It's gonna be a general rule. You can assume excess. Oh, sorry, that's my abbreviation for excess, because it's just XS. Unless 1 equivalent is specified. Okay, very rarely is, in the real world, is it ever 1 equivalent. Yeah, you guys have probably seen that in lab, right? Where you're usually doing reactions like 1.5 equivalents or 1.2 equivalents. It's so that you have excess and drive the reaction. Yeah, great questions, just keep asking. Okay, so at some point the proton comes on and water is super duper happy because it can take the electrons away from carbon and leave. And when it does, it generates a carbocation and we make an equivalent of water at this point. Okay? And nitrogen, because it's a little less it's a lot less electronegative than oxygen, is much more willing to have a positive charge reside on it. So that means that the resonance form that forms here is a little bit more stable than with the oxygen. So we have a resonance form that forms that has the plus charge on the nitrogen. Okay? This is much more stable than the oxygen equivalent. Okay? There's also one other thing that makes this a little different than, bless you, with an oxygen at this point. Okay, let me go back and show you where we are with that. Okay, so if we were at the oxygen equivalent, we would be right here. Okay, there is no proton on there that I can remove to stabilize the double bond, right? There's no way for me to do that. Now, with the nitrogen, because nitrogen has 1 more bond to it, it does have a plus charge. A proton that I can pull off to neutralize. So your water molecule that's there, more of your amine, something will come along and act as a base. If you prefer water, go ahead and put that. It will act as a base, come along, pull off the proton, push the electrons back to the nitrogen, and that gets us to our final product. Okay. One of the reasons I'm using the nitrogen here, another equivalent of amine here, is because in order to drive this reaction, we tend to remove the water. So there's less and less water around as we pull that water off to drive the reaction to product. Does anybody know what this functional group is called? Double bond to a nitrogen? Carbon-nitrogen double bond. This is the imine with the I. So this is an imine. So we have an amine when it's got just single bonds to it. Double bond to a carbon between nitrogen and carbon, that is an imine. Okay, how do we feel about that? Any questions at all about this?
Wait till the resonance structure is what gets attacked or
Deprotonated, yes. To stabilize it, yeah. Exactly. So this is I know I keep saying this, but I'm kind of like giving you hints here. This is a very common reaction in biological systems because you have a lot of amines present, whether it be in your proteins or otherwise, that will condense with carbonyls to make things like this that are very reactive. So you'll see this condensation reaction happen a lot. So this is a condensation, we're removing water. Don't worry about that, that's why I'm not writing it down. But I just want you to know that if you take biochem, this will come up again. Okay. In order for us to form an imine, we have to have this proton here that can get removed, okay? Which means that our nitrogen had to come in with at least two. It loses one here, it loses the second here. If it doesn't have two protons to lose, something else is gonna happen, okay? Some other way for us to stabilize this intermediate. And what we find is that we will form not an imine, but a different functional group where we have a double bond, but now it's between what was the carbonyl carbon and a carbon next to it, and that nitrogen will have all single bonds. So this is when we have only one hydrogen attached to the amine coming in. This is a secondary amine. So it has one hydrogen and two R groups. Those R groups don't have to be the same. Okay? And this functional group, which has an alkene and an amine, this is where Downey would do a puppet show. Did anybody have Downey for 205? Okay. Did he bring the puppets out in 205 at all? Okay. He would have two puppets out and he would go, there's an alkene and an amine, amine. This is an amine. There's some great videos of Downey on YouTube. Don't tell him I told you that. But he does a lot of puppet shows and they show up. I used to post them on Blackboard, but now I've lost them. I have to find them again. Okay. So the reason why is that when we get to an intermediate that looks like this, we are going to have two R groups on the nitrogen, and we can't stabilize that by pulling a proton off of the nitrogen. So I'm going to quickly go through the mechanism until we get to that point, because it's the same thing we did above. Okay, so oxygen grabs a proton to become our super electrophile. Okay, super electrophile now will attract our weak nucleophile, which is our amine. So that lone pair is attracted to the carbon, electrons go up to the oxygen. We are at an intermediate which looks like a nitrogen version of a hemiacetal. So it's kind of a hemiaminal. We do a proton transfer to make our leaving group. And the leaving group will leave. And to be consistent with how you learned it before, lone pair comes down from the nitrogen, kicks off the leaving group, which is the water. And we make a positively charged imine, which is called an aminium ion. Okay. So I did that really, really fast because it's the same thing that we did above, right? I'm going to pause here because I know I did that super fast. So now we are at this positively charged imine intermediate. Okay. Give you a second to catch up here. We're doing okay so far? Okay, good. Okay, good? All right. So if I used a primary amine or ammonia, I would have an extra proton to pull off. Now I don't, okay? So unlike oxygen, where the oxygen nucleophiles would then come in and we'd make the acetal, the nitrogen can hang out here for a little while, okay? And it can hang out here for a little while, and what will happen is that we will do an elimination reaction, okay? So this is very similar to the eliminations that you did back in 205, where something, you can use water if you want, or another nitrogen. Oh, sorry, I've put all these ethyl groups on because of the last one. These are just R's. R hydrogen. These will come along, and it can't pull off a proton on the nitrogen, so it pulls off one from next door. Why? Because the electrons that are in that carbon-hydrogen bond can come down to make a pi bond, which breaks the adjacent pi bond, and the electrons can go up to the oxygen. Yes?
Is that hydrogen in the methyl group, or is it just a hydrogen?
It is it's one of the hydrogens that is on this methyl group. Yes. Good question. Okay. Is showing it that way okay? We're good? All right. And what that does is that generates our enamine. And we regenerate our acid. And we generate water. Water is generated right here. That's where it's not, for some reason, this is not doing different colors up there. Does this work? Yes, okay. That's where that's being generated. Okay, yes?
So why can't you argue that the same thing can happen with the first?
Why can, okay. So the question is, why can't I pull off the proton here? Yeah, and make the enamine? It's not that it can't happen, but what I would say is that the imine here is going, how do I explain this in a different way? I think probably the best explanation is that the bond that you're forming here, this imine, this carbon-nitrogen double bond, is stronger than the carbon-carbon double bond. And I can get some numbers and bring them back to you if you want. to show that going from here, where I pull off this proton, to the imine is a more favorable pathway than forming the enamine of this, on this intermediate here. Okay? So in order for this to be the favored pathway where we deprotonate on the nitrogen as opposed to pulling off here, it has to be some kind of a lower energy transition state to go through or a more favored process. So maybe it does pull off that proton, but then gets reprotonated and we eventually go back here. Okay? So I can't tell you it 100% doesn't happen. Okay, great question. Good? Okay. So the next reaction, I kind of went back and forth about whether or not to revisit it, but since it's making an ester group, which we'll use in carboxylic acid derivatives, it's a very useful one to know. And this is the Baeyer-Villiger oxidation. Is this one that you've seen before? Okay. So, sorry, my computer keeps locking on me here. So the Baeyer-Villiger oxidation is a way for us to change oxidation states. So we are literally going to take a carbonyl and we're going to introduce a new bond between that carbon electronegative atom. That's an oxidation. So this is the Baeyer-Villiger oxidation. Do you remember how to do it? Meaning, do you remember what reagent does this? MCPBA. Okay. So MCPBA. So MCPBA does more than just epoxidize, right? I know Downey has a song that goes with does he still sing the YMCA song for MCPBA? No? He does? Okay. I won't sing for you. I cannot sing. I'm a horrible singer. So MCPBA in general is a great oxygen donor. Okay, and that is because MCPBA is what we call a per acid. It is metachloro, so go over your aromatic nomenclature. Metachloro per benzoic acid, so that means that the chloro group and the benzoic acid group are going to be meta to each other. Okay. Benzoic acid would say I have a carbonyl and an OH group attached, but this is per benzoic acid, so there's another oxygen. This is MCPBA. Metachloro per benzoic acid. Okay, so these oxygens, ooh, that's supposed to highlight there. These oxygens right in here are super reactive. Oxygen-oxygen bonds in general are very reactive. So we use MCPBA a lot because it is a per benzoic acid that is a little less dangerous than others. And it is going to donate an oxygen. It's going to donate an oxygen in such a way that it will stick that oxygen in between the carbonyl carbon and its most substituted carbon adjacent. Let me write that down. So the oxygen could go, the oxygen could get placed between this carbon and the carbonyl carbon, or it can get placed in between this carbon and the carbonyl carbon in this bond area. Okay? This one is going to be the one that's favored. And that is because the carbon adjacent to the carbonyl carbon is more substituted. Carbonyl carbon is more substituted. Okay, so if I were to break, I'll just use this nomenclature. So this is a tertiary carbon, this is a primary carbon. So sticking the oxygen between the carbonyl and the primary carbon is going to be unfavored. Okay, so, yeah.
I just had a question. I thought she told us that if there's an H, it's the one that is going to be automatically favored over, like, even a...
For an aldehyde, you mean?
Yeah.
Yeah, that is true for aldehydes. These are for ketones specifically.
Oh, okay.
Yeah, it's always going to be between the carbonyl carbon and the most substituted carbon. Yeah. Okay? So this is going to be your favored product versus where we put the oxygen in between the carbonyl and the methyl group. That is going to be not formed. All right, so I don't want to spend too long on the mechanism, but I want you to see how that oxygen gets transferred. So I put most of the mechanism here, but we're going to do the arrows as we walk through it, but just to not take up too much time and let you focus on what's the important thing. So MCPBA is an acid, okay? So MCPBA is going to generate H+. Okay, so do I want to write it like this? Yeah, I'll write it like this. So these are acidic conditions. Acidic conditions. Okay. So the first thing that's going to happen is our oxygen, because I'm under acidic conditions, is going to grab a hold of a proton. And that is going to generate our super electrophile. Okay? So I'm going to color code some things here. I'm going to color code the oxygen down here. All right? And I'm going to color code the oxygen of my carbonyl, just so that we can follow what's happening here. Okay, so we made a super electrophile. Our MCPBA is going to use a lone pair on one of the oxygens, the terminal oxygen, to attack the carbonyl carbon, pushing the electrons up to the carbonyl oxygen. Okay? So this is very similar to when we were doing acetal and hemiacetal chemistry. Okay? So now we have a new intermediate where the oxygen that attacked has a plus charge, and we've neutralized the carbonyl oxygen. Okay? Now we're going to have a proton transfer event undergo in which the proton moves from the oxygen that attacked to the oxygen next door, which is going to put a plus charge on that oxygen. Okay? Once again, acidic conditions, protons are coming on and off and on and off and on and off. What I hope I'm giving you is the freedom to say, I'm under acidic conditions. If I need a proton, there's protons around. If I need to get rid of one, I can get rid of one. You have that freedom. You have that carte blanche, okay, to do whatever you want to. All right, so what we've done now is we've generated a really good leaving group. This right here is a leaving group. And this next step is kind of strange. This is going to remind you of your alkyl shifts of carbocation rearrangement fame, okay, where the more substituted carbon is going to take the electrons right now that it shares with the carbon, and it's going to move next door. The reason why this is going to work is because the carbocation that we'll be forming is resonance stabilized. So the oxygen, this blue oxygen is going to share its electrons, which allows the alkyl group to take its electrons and shift next door. Why does it do that? Because we have a very reactive oxygen-oxygen bond, okay? That oxygen that the pink one is attached to has a positive charge. We've made it even more reactive. It wants to break that bond, something fierce. So when the R group moves over, that causes the leaving group to leave. Okay, you can do this in 2 steps if you want to. Did you guys see it like this? Maybe. Okay. The other way I've seen people do it is they'll have the migration and the leaving group leave and then show the resonance coming down here. Okay. So what we've done now, and I kind of tried to keep all the atoms where they kind of were, is we've lost the leaving group. The oxygen that came from the peroxide is now in between the carbonyl carbon and the alkyl group that migrated. And we have a positive charge that has to get pulled off. Make sure we're still recording. Yep, we are. Okay? So once we have that migration happen, we now have our ester that just needs to be neutralized. So we could have anything. Usually this is wet, so you could use water. So let me just make a little statement up here. Water is usually in here. Okay, it keeps the MCPBA from exploding, literally. Okay, so water can act as your base, pull off the proton, and liberate here our product. We generate the benzoic acid as a byproduct. So this is the benzoic acid. We generated that benzoic acid right here. That was our leaving group. Okay. And we also, sugar booger. We also generated H3O plus, which is basically our catalyst being regenerated, which is H plus water. Okay. So this gives us one access to esters. It also talks about the weakness of the oxygen-oxygen bond, especially once it gets protonated. Though that was a really weak bond and we want to break that, force that apart. So this MCBBA is a great source of an oxygen atom for this reaction. Okay, want to do just a quick few problems because I feel like these problems kind of highlight some of the ambiguity in the reaction. All right, so in the case above, we had the choice of either migrating a methyl group or an isopropyl group, okay? It's a little clear in this one, like which one's more substituted, okay? In these two below, I wanna highlight the fact that the one on the bottom, I have 2 carbons that are tertiary, so which one's gonna migrate? And this one, how do we deal with a ring? Okay? All right, have you seen these kinds of examples before? Maybe? Okay, so let's deal with the first one up top. So we have MCPBA, this is gonna be our source of our oxygen, and we have a carbonyl, which means it is going to transform the ketone into an ester. So we're gonna take the ketone, and we're gonna transform it into an ester. Okay, so the question is, which of the carbons next to the carbonyl carbon are the most substituted? So what is more substituted? This one to the left or this one to the right? The orange or the, what colors are they showing up there? Orange or green or red or green? Which one's more substituted? The orange or the red one, yeah. So this is the one that's most substituted. So that is the one that will undergo migration in the mechanism, which means that the oxygen is going to get placed between those 2 carbons, the carbonyl carbon and the more substituted carbon. Okay? The rest of the structure going right from the carbonyl carbon is going to remain unchanged. Okay? So that means that we started with a ring, we're gonna end with a ring. All we're gonna do is we're gonna stick the oxygen in between these 2 carbons. So how big a ring am I forming? A 6-membered ring, right? Because we're gonna stick one more atom in it. So I'm gonna have a 6-membered ring that has an ester within it. Okay, why I drew it that big, I'm not sure. The carbon next to the oxygen within the ring is the one with the methyl group. So if I number 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, we're gonna stick the oxygen between the carbonyl carbon and carbon number 4, and carbon number 4 keeps that methyl group. How do we feel about that? Not too bad? Okay. Let's take a look at the next one. We have a carbonyl carbon, we have MCPBA, we have 2 adjacent carbons. They both have 3 carbons attached to them. So the question is, which of those is going to migrate? The rule is that if you have the same substitution, but one is aromatic, that aromatic group is going to migrate preferentially. So this aromatic group is going to migrate first, or preferentially. So that means the oxygen gets stuck in that bond. So we form an ester, and that oxygen is placed between the carbonyl carbon and the phenyl ring. Okay, so I picked 2 that are kind of weird ones to kind of just make sure I covered the examples that tend to be the more confusing. The crazy ones. Good? Awesome. All right. Last part of carbonyl chemistry is the reaction of carbonyls that have double bonds next to them. These are carbonyls that are conjugated. They have what we call the alpha beta unsaturation. So there are positions next to the carbonyl that we give letters to. So right next door is the alpha carbon, then we have beta, then we have gamma, and then we have delta. And then it just goes alphabetical, epsilon, and I don't know the rest of the Greek alphabet, okay? Alpha beta are the ones that we're gonna use the most. So if we have an alpha beta unsaturation, then that means that we have a double bond between the carbon next to the carbonyl and the carbon next to that, okay? It's just easier to say alpha carbon than the carbon next to the carbonyl and the carbon next to that, okay? Important thing to know about an alpha beta unsaturated carbonyl is that there are different places where charges are going to be present, okay? And that is due to resonance. So we have one resonance form where the carbonyl pi bond electrons localize up on the oxygen, which gives us a negative charge on the oxygen and a plus charge on the carbon, okay? And we have additional resonance form. Here I have a double bond next to a carbocation. That can resonate again, and the pi bond moves over, and we generate another carbon that has a positive character to it, which is the beta carbon. So if we think about the electronics of the alpha beta unsaturated system, I have a delta minus on the oxygen, and I have 2 positions that hold positive charge. One is the carbonyl carbon, and the other is at the beta position, okay? Which means if you're a nucleophile, you have choices, okay? You guys cover this? Okay. Oh, new stuff. Okay. So nucleophiles that like to add to the carbonyl carbon are what we call 1,2 addition products. So these are nucleophiles that add to the carbonyl carbon. And there are going to be nucleophiles that like to add to the beta carbon. And these are going to be called 1,4 addition products. These are nucleophiles that prefer to add to the beta carbon. Okay. All right, that's cool. We have something new here. All right. So the way that we can kind of remember these in general is that our carbon nucleophiles and our hydrogen nucleophiles like to add to the carbonyl carbon. So these are going to be H- and R-. So we have our hydrides, which are your sodium borohydride and lithium aluminum hydride. Okay, those are the two we're going to focus on. Your carbon nucleophiles are going to be your Grignards. I feel like we should clap. Organolithium reagents. And there's one other one that I didn't review because it sounded like you guys knew this one. And this is your ylide, which comes up in the Wittig reaction. Okay, so that is where we have a negatively charged carbon nucleophile that has a phosphorus next door. Okay, you guys remember Wittig? Yeah? Okay. So what we're going to pick up on, what day is today? Today's Thursday, right? On Tuesday, we're going to talk about carbon or nucleophiles that add 1,4 and maybe introduce cuprates. Have you guys done cuprates? Okay, we're going to do cuprates, some synthesis, and then we're going to get into carboxylic acid derivatives, and we're not going to spend tons of time with those, okay, because you guys did pretty well with that exam. Good? All right.